ML Platform Meetup was founded by ML infrastructure and platform engineers from various tech companies. It provides a forum for engineers across this company to share and discuss their work. Welcome everyone to join the fourth edition of ML Platform Meetup. My name is Joseph. I'm an Uber AI platform microangel engineer. I'll be moderating today. First, I would like to thank Uber's tech brand team, Christina and Sarah, for helping us with logistics and coordinating across various different teams. We would also like to thank the presenter for sharing their work and take time to prepare the slide. Here are the agenda. We have 2 parallel tracks till 4 o'clock with few 10 minutes break. See the registration page for additional information on the schedule. So let's go over some logistics. For raffle winner, please check your email to confirm your Uber account email address. For presenter, please mute when you are not presenting, and please read out the question in the Q&A window before answering. And everyone, please post your question in the Q&A window, and please annotate the question with session and talk. So our first talk will be from Intuit. Can
we start?
Yes, please.
Okay. Hey everyone, thanks for joining this meetup. Please share. Hello everyone, my name is Vijay. Remember in the olden days, we had these cassette tapes. In a cassette tape, when you had to listen to a song or a track which is on track 5, you actually had to press forward, from track 1, go all the way to track 5, and then hit resume and play. Sometimes you would go forward too far, and then in that case, you'd have to do rewind, and basically you have to do this a few times before you actually landed on the beginning of track 5. And that's when you would hit resume and play the song at normal speed. So backfilling is kind of like that. So my name is Vijay, and we have Ratul and Harish. We are from Intuit, and we are here to talk about how we implemented stateful backfill capability in our platform. This is the agenda for today, just a quick glance. To set the context, this is the view a data scientist and ML at Intuit experiences. This is the ecosystem in Intuit. So data from applications, both real-time and batch, flows into its data lake through Kafka platform. That's the real-time data flows through the Kafka platform, and all the batch data goes through the batch processing pipelines and into the data lake. Once the raw data is available, the data scientists and MLEs, they use Intuit's data processing platforms to create features. This platform supports both stream and batch processing. So using this platform, they write code to transform this raw data and create features. If the features require a local state, then the platform supports the state as well, which they can use to create stateful features. Once the features are created, the features, they are stored in the feature store, which is supported by the feature management platform at Intuit. And it has both online features as well as offline features. Then they move on to model training, development, and deployment, for which they use the model hosting and execution platform at Intuit. Once the model is deployed, applications can now integrate with the model, and they can call a model endpoint to evaluate the model or to execute the model. In that process, in real time, the features from the online store is fetched and sent to the model. The model is evaluated, and the results of the model are returned back to the application. So as you can imagine, model development is an iterative process. They go through the several phases, creating features, creating the model, deploying the model, and evaluating the model. And each of this phase itself is iterative in nature. When they are creating features, they would have to transform the source data, create features, evaluate the features, and until the features are valid, they would have to repeat this process. Now, consider the following use case or a scenario in Intuit. Intuit is a company that handles huge amounts of financial transactions. So it's of utmost priority for the company to identify and prevent fraudulent transactions and users. And there are several models that are deployed in production to do this task. As an example, I'm going to take just one model, which requires, among many features, one of the features is to count the number of bank accounts attached to a user added by the user into one of the Intuit products like QuickBooks. So these counts are, counts by different entity keys, like user ID, and bucketed by by different time ranges, like last 24 hours, 30 days, global count. So essentially, these are stateful features. The value depends on the user action. So anytime a user adds or removes an account, this the total count is maintained by different period of times. So in order to create these features, the data scientist would, create this code which reads from a real-time source, and as and when an account is added or removed, the count is incremented or decremented using the local state here, and that's why these are called stateful features. Now consider a situation where either the model requirements change, or there's a bug in the model, or they discover that new features are needed. In that case, they would have to go back and either update the code to add new features, or update the code to fix existing features. Now, since these are stateful features, they cannot just update the code and deploy the pipeline. They would have to first process all the historical events in the same order that they originally occurred. Once after all the events are processed and the features are calculated, only then they can switch to the real-time source. The reason they have to do this is because, like I said, these are stateful features, and the counts are calculated, based on different time ranges. So, count by 24 hours to get a count by 24 hours, it has to be, the same events need to be replayed in the same order. So we also need to make sure that, an event is not processed more than once, and we also don't miss any events. So for a use case like this, for fraud detection, they would have to process at least, like 2 years worth of data from 2 years of historical events, which is around 40 terabytes of data. And the state created in the process is closer to 90 or 100 gigabytes. So this takes, they need to be, because this is an iterative process, they would need to do this many times, and they have to, they would like the process to be finished in under a few days to process over 2 years of data. So in a nutshell, the customer problem is, as a data scientist or a machine learning engineer, I'm trying to bootstrap stateful features, but there's no way to process historical data followed by real-time data in the same pipeline. And historical data need to be processed in the same order in which the events originally occurred, and also need to make sure there's no event is not skipped, we don't miss any event, and also need to make sure we don't process any event multiple times. The platform provides a local state, but we need to make sure that the state is carried over when the source changes from historical to real time. Currently, the state is lost if the source changes. Because the platform currently only supports reading one source at a time. So this makes me feel unproductive and stuck, and essentially I cannot do feature development, and hence I cannot do model development also. So ideal solution or ideal state for me is the platform provides a self-service capability where I can specify both the historical data source and the real-time data source, and it switches automatically, from one source to another, and also maintains the state while doing so. So the biggest benefit is I can quickly iterate with feature development and do backfill at a very low cost, which makes me feel productive and efficient. And this is very cost effective and is a very efficient way of doing stateful feature engineering. Next, I will pass it on to Ratul, who will go into the details of the capability.
Thanks, Vijay. Let me share my screen. Okay. Hello, everyone. My name is Ratul. So today I'm going to talk about the backfill, and then what is state, which I mentioned about the state, and then we'll talk about the components, the features of the backfill. Okay. So let's start with how the backfill works and what is backfill. So if I plot event time and processing time on X and Y axis, then the dotted line, which is a 45-degree angle where X equal to Y, it will tell you the ideal line. Okay, what is the purple line? Purple line is at the near real time. That means whenever the event is appearing, you are processing in some millisecond delay. Okay. Now, what is the blue line? So blue line is at the backfill line. So what is this point? This point means in some processing time, which is Wednesday, 7 September, around 1:18 p.m. this time, we have start processing last 2 years of event data. So 2020 September data, we started doing the backfill. So the blue line, if you see, the blue line has to be more inclined to the x-axis event time, and it has to catch up with the streamline. Either it has to catch up with the streamline or it has to be close proximity. What is the close proximity? Whenever the backfill finish, that time should be within the time range of your Kafka, the stream retention, right? Now, we'll talk about what is switching to stream, but let's understand the backfill has to catch up with the stream. That means in a small processing time, you have to catch up with big event time processing. For example, what we have done, in 4 days, we have processed last 2 years of data. Okay, so we need more throughput and the process has to be fast enough. So let's now move to the backfill types. First, stateless and stateful. Stateless, let's talk with the example. If you wanted to extract the query parameter from the URL, that's a stateless. How we can do that? You can have 2 pipelines, one to process the historical data, another to process the stream data. What is the commonality? Commonality is the sync. They are writing to common sync. Now, they doesn't have to be 2 separate code base. They can have 2 same code base with just if-else block. Either first you can connect to historical data and then to stream. Now let's talk about what is the stateful. Stateful is that the replay historical data to build the state and join it with the stream. Why the state matters? Because we are talking about the local state that the beam maintain. It can be either RocksDB or file system, but not the external state, Redis or DynamoDB. So whenever we are talking about the local state, the application is maintaining, what matters is that the unified pipeline, because you don't have the flexibility to change the pipeline. So the pipeline has to be unified, and the same pipeline needs to connect to historical data, process it, connect to stream, process it, and then only the state will get carried forward. Otherwise, if the topology gets changed, you cannot recover. Okay, so we mentioned about the state. Just 2 sentences about the state. Let's say if the event coming, we have the quantity equal to 1, and you wanted to maintain accumulator called cumulative quantity. Okay, so I maintain the accumulator cumulative quantity that is equal to 1, event out, quantity 1, cumulative quantity 1. Next time I got a quantity equal to 9, the accumulator needs to be updated to 10, 1 plus 9, and event out will be cumulative quantity equal to 10. So the state, the middle column, that is the that we are talking about, right? So for example, count of visitor, right? So that is state. Now the feature of the backfill, and we got this list of feature from our product management, and then we implement the backfill based on that. So let's walk us, I can walk you through what is the features. First and foremost, config-driven self-serve. So we 3 are part of the platform team. We want our user to do their job independently. What Vijay mentioned, it has to be a repetitive process, so they can do in their time zone independently. Next thing is that bounded and unbounded backfill. This is our terminology, but I can explain. Bounded backfill, you provide the start date and the end date. So let's say you said, I want the backfill to process, the historical data to process between the 1st April 2020 to 1st May 2020. It will do the processing and it will stop there. Unbounded backfill, on the other hand, you just provide the start date. It will process whatever historical data you have in your historical store. For our case is S3, and then it will switch to stream. We'll talk about more. Stop, start, and restart experience. That's very vital. So you start the backfill, and after 4 months of backfill, you stop the pipeline because you wanted to validate the data. Backfill is costly, by the way. Costly in the sense you are processing last 2 years of data, right? So that's a terabyte of data. So you don't want any mistake to happen. So you stop the pipeline. After after 4 months of processing, you wanted to validate the data. If everything is fine, you wanted to resume it. Our stream processing platform has a capability called offset, deployment offset. If you keep the same deployment offset, backfill capability exactly know the resume point. It will start from the last stop point. After 4 months of data validation, if you see something is wrong, you wanted to change your code, reset the backfill, only upgrade the offset and redeploy. It will start from the day 0. Okay. The next feature is automatically switch to stream. That actually we like the most. In the unbounded backfill, first thing is that it will process all the historical data, and then the backfill capability, the SDK exactly know when the backfill is done and no more historical data present, then it will automatically switch to stream. We'll talk about more on this automatic switch to stream. Event ordering, that's specific to Intuit. We have a use case like for a like what Vijay mentioned, for an auth ID, we wanted to know how many account has attached last hour, last 2 hours, last 3 hours, like that, H-0, H-1, H-2. So the ordering matters. So we wanted to process 8 o'clock data, 8 p.m. data, maybe some time in past before processing the 9 p.m. data on the same day. Okay. Next thing is that no overlapping interval processes. Like our use case is very disjoint, like H-0, H-1. So we wanted to make sure that we are not, backfill is not picking up 9 o'clock data. 9 o'clock means that hour of data before finish processing 8 o'clock data. So the way the backfill works, it will pick up hour by hour, 7 o'clock, 8 o'clock, 9 o'clock, 10 o'clock, like that. Okay. Scalability. When if you remember, backfill has to be fast and high throughput. So the scalability during the backfill, what we have done is that we increase the cluster size. For example, 40 nodes. After switching to stream, automatically switching to stream, we reduce it to 4 or 5, whatever works for us. Okay. Now backfill switch to stream. So if you see in this diagram, the upper rectangle is at the S3 archive location, and then the green one is at the stream. So the blue dot that is going, that is the event line. So we start from the cold event and it's keep getting warmer. And then if you see this line, it will actually switch to stream. Now, what matters is that the backfill capability exactly know when it left processing of the historical data, and it will, based on that processing, it will pick up the Kafka offset. Now, your Kafka latest offset may be some minute or second ahead, but whenever it switches to stream, it will start from the offset. So why this is required? This is to make sure that there is no data loss and there is no duplicate data processing. So the backfill capability will do the synchronization. Where it left in the backfill processing, it will pick up from the exact next millisecond in the stream processing. Okay. So saying that, I will hand it over to Harish to talk about the capability journey, how the software evolved and the architecture. Thank you.
Thanks, Vijay and Atul. Hi, I'm Harish I'm from Stream Processing Platform at Intuit. As a platform, we provide our main customers for this platform are like data engineers, data scientists, and machine learning engineers. So we need to provide like necessary tooling and operational guidance for the customers and infrastructure to develop their streaming applications rapidly. As mentioned, as shown in the diagram, like all that customer needs to focus is like as a tip of iceberg, their business logic. They have to come and like code, and it will be hosted by hosting, and everything will be taken care by our team. As a stream processing platform, like these are our offerings to customers. So the main offering is like we are giving is Beam on top of Link if customer wants to use stateful applications, and we are giving like a Spark also as another offering, like both PySpark and JVM Spark. And some customers onboarded to this platform, like out of the box, like we provide all the necessary operational guidelines like Splunk logging and default dashboards in Wavefront. And this entire application is being clusters, like being hosted in EKS. So these are all these things will be abstracted from the customers. Only they need to focus on their transformation logic, like how to transform the data and use it. And we also provide some necessary SDKs
that so that customers can connect to Intuit streaming systems like Kafka. And if they want to connect to a data lake S3 also, they will connect using this SDK. So let's go through the platform guidelines for stateful backfill use case. So whatever the solution that we provide, it should be low cost, and it should use the local state that is being provided by default by Beam or Fling. So as I mentioned, like our default offering is Beam on top of Fling for the stateful applications. We need to provide like SDK that talks to like our we use Intuit our own managed Kafka, and this SDK should supposed to connect to this Kafka brokers automatically. So customer by click of a button or like configuring it in a runtime configuration, they should be able to use this automatically. And one of the main use cases like customer should be able to use like same transformations, same code, you can say, for both backfill use case as well as streaming applications. They should not do anything extra. And when we are doing this application, like we need to be mindful of like there should not be any duplicate processing, and the entire application should be fault tolerant. So, and it should be scalable. Like in backfill use case, like we need to throw like a lot of nodes to process the data very fast and efficient way. In streaming use case, as the traffic would be less, we should be able to reduce the nodes so that the cost, we can reduce the cost on that front. So when we started this problem, like I'll explain a little bit in how Intuit data systems are like. Okay, we have like our default streaming application, streaming system as the Kafka, our own managed Kafka, and we maintain 2 years worth of like data in data lake for this topic, so that if there is any application error happens, customer needs to reprocess the data for certain timestamp to timestamp, they can use this S3 data. And this is all like if I want to reiterate the problem statement, like now like we have two sources. One is like data lake S3, and then we store the data hour by hour. And when this backfill a stateful application, as ordering is like one of the necessary for us, so that it is like we want to process the data as like it is producing from Kafka, but we need to read from S3. So that's where like ordering is needed to have the like accuracy in the models, fraudulent models, or any model that customers are using. So given an example, let's say like we want to backfill like this system like from morning 9 o'clock. This is how it will be like. Okay, from data lake S3, it should start reading from 9 o'clock data, and then it should then read to 10, 11 o'clock, or 12 o'clock. Once that is done, it should read from Kafka source from exactly like 1 o'clock. So we can get this done using offsets, Kafka offset. So when we started looking at this problem, like it looks like challenging and like for us interesting and challenging, because like Beam, as mentioned, Beam is our default offering for the customer for stateful applications. Beam doesn't have 2.2 and doesn't have any support for hybrid source where it can connect to two data sources. And we can achieve this using external source. Like after reading entire S3 data, we can put the state in some Redis or some external store and read it while bootstrapping it from Kafka. But it comes with like lot of manual effort, as well as it's a high cost solution. So we didn't pursue that one. And the event should be processed in order by order. That means like when you are processing an S3 data, we should be mindful of like when till what time like we have read the data, and what is the next data we need to read. An entire solution should be used across the Intuit. Like should be customer should not worry about like the underlying implementation of this one. We provide like as a reader, like hey, this is your backfill reader, which will take care of everything to them. And then they need to mention that what is the topic they want to backfill and what is the data like S3. These are all the offerings we need to provide. Like, and when we started, so I'll quickly go through the like evolution of this use case. So when we started, the first one is like we are, as mentioned, like Apache Beam is our streaming processing model. So first, like one of the approach we tried is like we started reading from S3 and created the state, and we changed the source on the fly and try to use the same state. But we are not able to use that when the state is getting invalidated. Either it is working well in backfill mode or it is working in stream, like, but the interaction is not happening. So we didn't get that solution. We found like another solution. So creating like intermediate topic where we replicate like all the S3 data into this intermediate topic. Once that is done, we started reading the Kafka real production Kafka data in real time and then push that data to this intermediate topic. This solution worked for us, but here like we are introducing extra one more intermediate topic which is unnecessary, and it is comes with a cost, and we need to maintain like another job to replicate all this data. So we didn't pursue that one. Finally, like we found out like two solutions. One like require like little bit of manual intervention, and another one is like doesn't require. So the one which requires manual intervention is like working with all the features of Beam, like timers and all. So in this solution, there are two topologies would be there. Like first topology would tries to read from S3 and then build the state. Once everything is done, customer will stop the pipeline and will change the configuration parameter, like, hey, now I want to run the streaming mode. Then it connects to Kafka topic and then use the state that has been built in previous backfill mode, and then we'll write the same state. So this way, that was like one solution. And another solution is like it doesn't provide any timers of Beam timers, but there is no manual intervention is needed in this one. So we created our own dual source where it is able to read from S3 and maintains the offset, like how far we have read. And once entire data is finished in S3, then it will switch over to Kafka and read from that particular timestamp, like where it left reading in S3. We were able to build that state, and then seamlessly it will be used across both backfill and stream. And there is no need to stop and start for this approach. And yeah, this solution is being used by one of the customers at Intuit for the fraudulent use case. And these are all some of the details of the production run. So customer were able to read like 40 dB of data, like S3 data within 2 to 5 days. So based on their transformation logic, like low transformation logic, it is quickly done in 2 days, and with high transformation logic, they're able to do it like in 5 days. And the state size is around 100 GB. It is coming around. As mentioned, like Flink and Beam like automatically gives us like state, like local state. We reduce like a cost on that front. So if you see that previously solution for us, like we use Redis for maintain the stored state. Now as internal state we are using, so the cost has been reduced effectively from $400K to $50K per year. And we are expecting like more use cases to onboard with this solution. And as a next steps evolution of this process, when we started developing, like there are no ready-made solutions available. Like we reached out to Beam and other communities, we couldn't find like the hybrid source. But after a few months, like we are into this solving this problem. Like Flink has come up with their own hybrid source, like in 1.14 version. We built that solution as well, or we are hoping to use that solution for this backfill use case. With that, I'm concluding this presentation. Please let us know if you have any questions.
Okay, thank you. Next talk will be from Meta engineer talking about query optimization.
Sorry, just give me 1 second. Okay, hi everyone. Today, along with my co-presenter Hanuman from Meta, we're going to be talking about SKU optimizations in F3 by Meta. And F3 is the platform being used in Meta for feature engineering. So this is really a cross area between maybe feature engineering, data infrastructure, query optimization, but it's really an interesting perspective where we care about query optimization not at the compute engine level or at the DBMS level, but also on the feature engineering platform as well. So we'll talk about some background and scope, and we're going to talk about what kind of optimization problems that affects reliability, efficiency in F3, and what's the solution we have adopted, and what we are working on next steps. So I guess everybody knows what is feature engineering. It's it's mainly about extracting information, useful information from raw data, and present that to the ML algorithms, right? So, and ML AI is crucial to Meta. It's crucial for everybody. This is something being really moving very fast in all aspects of the industry. Examples of AI ML is recommendation engines, AR VR experiences, content integrity, trying to automate checking the integrity of content without reducing human interaction. So again, there are so many feature engineering platform solutions at Meta. So what is called F3, and that's the group I work and along with my co-presenter, this is the kind of the proposed platform for consolidation of different solutions. And one of the key differentiator here is really the privacy, and it has a declarative interface. So you could, for authoring, there is a language that are used for authoring features. It's also serving as a compiler that serves batch features, streaming features, and different kinds of features. So this is a very high-level view of the F3 architecture, or the flow that being used by F3. So we have the F3 compiler, and the F3 compiler takes a declarative request for creating a feature and deploying it. So, and the output of the intermediately, there is something called generation pipeline, and that's for the most part is going to be a SQL, and we have something that a wrap around SQL that produce pipelines, and once that get executed, so this is the generation that one produce involves joins and aggregations. Working with the raw data we talked about. There is something that really extracts the final results for the DAG engine, and then you go off to the machine learning. So our focus really here in this talk is about what's called the generation, and I have it in a different color here because this is where most of these optimization problem happens. But without maybe going deep into how the F3 compiler works, there is a phase in the F3 that executes joins and aggregations and filters, all these DBMS operations on behalf of the feature, and that's a crucial part of the overall flow of the feature engineering here. So what we are trying to do here, we're trying to talk about the reliability efficiency problem we have with this generation phase. And in our case, for the batch track, this is mostly queries that we run on Spark SQL. So Spark SQL, we have efficiency and reliability issues that affected the F3 feature flow here. So we focused. So initially we looked at this problem. We focused on batch that were mostly the common problems, and we have the batch. We have Spark. We have internal Presto. But as I said, Spark is the main engine we have used, and it did impact a lot of the use cases we have. So I'm sure a lot of you are familiar with what data skew means. I'm going to go through that through a simple example here, but really in any distributed system, and I think everybody here is using a distributed system, data skew, or some people they call it hot shards, and things like that is a very common problem, and usually is a challenging problem either from a platform perspective or from a DBMS perspective. And we have that too. I mean, you have, if you're talking about, let's say, a user, you may have a popular user that has lots of data. And if you're partitioning by user ID, then you end up by skew. So that's a typical, very simple case. So let's look at this join here. So we have an outer join between, say, T1 and T2 on some join condition, A equal B. And in many cases, in order to do this join, you are going to shuffle both tables on the join column. There are cases where you don't, but frequently you do, right? So just going through this example, illustrating how the skew here is that if table T1 has a billion row, and the A column from T1 has a million unique values. So this 1 billion rows spread around 1 million values. So every value has a frequency of 1K. So that's maybe very simple math here. And say in a distributed environment, you have 100 tasks. So each task gets an equal number of rows. Well, it's, that's maybe the plan, is that it gets, each one will get like 1% of the data. However, if you're distributing on the join column, that's not going to happen, because there is some values that have a lot more rows than other values. So let's say you have a value V1 that's very, very frequent. And I said maybe user IDs and maybe user ID of for influencer, for example. So if the value V1 has a frequency of much more than 1K, the average, then all the data for that V1 will go to one task of these 100 tasks, and that will dictate the latency, right? Because in a distributed system, latency is dominated by the last task, right? So I hope this example is a simple case. I'm sure a lot of you know about what data skew is, but that's maybe a very generic example of showing that. So the bottom line about skew, usually it's about latency, right? And this is where the problem is. And if you're talking about aggregation, it's a similar problem too. So in our case, like the underlying engine, the Spark engine, there are solutions for skew, but they were not adequate for us. I think maybe the use cases we have are different and so on. So, and some of the solutions may be appropriate for a DBMS, but not appropriate for a platform like F3. So Spark has sufficient skew solutions through user hands. There is this runtime skew mitigation. Both requires manual intervention. Giving the code generation automation by F3, these are not appropriate as a solution. And Presto, the other compute engine we have, it doesn't have really a solution in the engine. It just like have some suggestions on how user can handle skew. So what we're thinking here is we need to build our own solution, and so some people will argue like, why you wanna do work on behalf of the BMS? And the argument we have is that if we handle some optimizations like skew, and at this platform level, it really gives us a generic solution for all underlying compute engines. I mean, you could add a compute engine for streaming, for batch, and you just want to make sure that you have addressed your optimization needs at this level. Other thing is that we have intimate knowledge of our own data. So F3, knows a lot about some of these use cases and some of the data itself, and can make customized optimizations at that level that will work very well. So it's like F3 is acting like a smart user, if you will. So this F3 platform I described briefly can actually apply these optimizations. So, okay, the bottom line, we decided to apply query optimization at the F3 level. So we decided to apply query optimizations at the feature engineering platform, and giving the capability of F3, we should be able to do it. F3 is acting like a compiler, so it has all the infrastructure for optimization. It has the notion of intermediate representation, just like for those of you who work in DBMS, like parsing trees, query graphs, that kind of stuff. And then we have targeted the specific use cases we have for skew. So we have built optimizations for null skew, which is very common, where the most frequent value is a null, or non-null skew, and skew based on top K. Top K here means the most frequent values. So once we talk about skew, we talk about values that are frequent or popular. So and also applying that for the group by. So basically, we are applying these optimizations as a phase in the F3 engine, if you want to call it that way. It's an engine, it's a compiler, by rewriting internally the DAG. We call it a DAG, it's a graph with directed edges. It's really a query graph, if you will. And we do transformations for those to apply the optimization. So Hanumat can pick up from here, talk about the specific rewrites we have done in the F3 compiler.
Yeah, thanks, Ahmad. This is Hanumat from Meta. So I and Ahmad are working on AI infra. Maybe I think you want to share, Ahmad? Yeah, okay.
I'll continue the sharing, and you just tell me to go to the next slide.
Yeah, sure. Thanks. So we are part of the AI infra group working on the F3 compiler, and I'll be talking specifically about the rewrites. So just wanted to reiterate again that these rewrites are done in the F3 optimizer, and we are doing these optimizations on the F3 IR DAG. So that means like any runtime engine can benefit it. So it's if you want to add a new runtime engine, we don't need to do these optimizations again and again. Given that, so let me go over the optimizations which we implemented. So the first one would be like I want to talk about is null skew. Basically, it's a skew value on the null values. So skewed on the null values. So generally, the pattern of in feature engineering applicable not just in F3 but any feature engineering platform is one of the observational data is on the left side, and the left order join is performed on the right side table. And the observation table is kind of a huge table where billions of rows are there. And let's go over an example on that where the condition is as simple as A equal to B. Ahmad, do you want to go to the next slide? Yeah. Sorry, back. Yeah. So given this scenario, so we want to transform that into a left order join with coalesce conditions. Sorry for the noise, I think. Yeah. So what happens is that we wanted to transform a condition of A equal to B where we want to distribute the null values across all the tasks. And we use the coalesce condition where we assign each of the null value in the left side and the right side by randomly assigning a value to that so that they'll be distributed across all the tasks. So this generally works for left order join and right order join, and inner joins don't need to take care of this because inner join you can as simple as implement a filter conditions to remove all the null values. Yeah, so by this way, I think we reduced our latency time for one of our customers, Instagram, from 68 hours latency to 2 hours. So all the pipelines after this optimization are well within 2 hours. Thanks. Yeah, next slide, Ahmad, please.
Okay.
Yeah, so given that the next general optimization is non-null skew. So we talked about the null skew, but the non-null skew is basically a skew on the non-null value. It's a more generic optimization, and it's skewed on the data value other than null value. And the rewrite is almost similar as the null skew, but with more complexity. And the idea is to distribute all the non-null values evenly across all the tasks, and all the data values are affected by this. So what I mean by the data values, I'll be explaining a little bit later after presenting the rewrite itself. Go to the next slide, please, Amit. Yeah, so the same scenario where left outer join is joining two tables, left side and the right side, and it is transformed into another DAG, where one of the right table is duplicated into 10 buckets. So each of the row is duplicated into 10 buckets, and the 10 can be changed. In our workload, our testing 10 was enough. And the left side of the table is assigned a random value. So each row will be assigned to one bucket based on the random value. And the condition which happens to be after the rewrite is A equal to B. Simple condition will be transformed to A equal to B, and A prime is equal to B prime. So where A prime is a random into 10, and B prime is based on the lateral join, which is performed by duplicating all the rows. So given this, like what's going to happen is that all the non-null values are distributed across all the tasks, and your latency will be decreased with a trade-off. The trade-off is efficiency is going to increase. And in our measurement, the efficiency which got increased is around like 15 to 20%. That's because all the values of the right side are being duplicated. That's extra work that's being performed. And also all the non-null, non-skewed values are also being participated in the redistribution. That's more of extra work that is performed by this rewrite. And the next rewrite, which I'll be talking about, kind of optimizes this, removes all the extra work that is performed by the non-null skew. That's called top case skew. Okay, so in our top case skew, basically our measurement is that, so generally what happens is all the values pertaining to any table falls into this distribution, where some of the highly skewed values are mostly limited, and all the other values are almost similar in frequency. And yeah, so go to the next slide, Amit. So the motivation for this top case skew is basically the observations which we have on the workload, basically the CPU versus latency trade-off, and most values are not skewed. So that's our way of putting it, like why this optimization is important and what is going to achieve. And each of this can be based on tuning the K itself, K topmost values. So depending upon your workload, you can adjust that K. And this is the example of the workload which was observed in our meta add ID column. Next slide, Amit. Yeah, coming on to the rewrite itself, basically the same pattern, the left outer join with the left side table and the right side table, is being transformed into a similar IR DAG pattern, which is almost same as the non-null skewed DAG, but with a few more expressions, the complicated expressions, like if top K. So the top K basically here happens to be one of the top K most frequent values. If the value falls into this one of those values, then we apply the rand function. Otherwise, we don't, we just leave it as it is. And similarly, on the right side duplication part, what we do is that if top K, if the value falls into the top K, then we distribute that value, we clone that value into a number of rows. That's here, it's 10 rows. Otherwise, we leave it as it is. And then the distribution happens only with the top K values. We are removing all the extra work that has happened in the non-null skew. And hence, in our measurement, what happened is that after this rewrite, it's almost as equal as in the efficiency wise, as equal as the base example without the rewrite itself. That means with the skewed values, but the latency is equal to the skewed optimization. So that means not clear. So we are getting benefits of both the worlds. Ahmad, next slide. Okay, so yeah, maybe I think this slide is not applicable for this. Yeah, so yeah, I'll be handing over to Ahmad now. He'll be talking about the Bootstrap store and where we are applying and how we are applying these optimizations in general. Take it over from here.
Yeah. Okay. Thanks, Hanuman. So yeah, I hope this in a high level is interesting to this group here. We don't want to do a quick optimization talk, but we try to do this from the perspective of feature engineering and the need for that from a feature engineering perspective. And so I guess, yeah, the skew optimizations that we just talked about is maybe one example. There are other cases which was the previous slide is talking about, but we actually, yeah, we don't want to go into that details. But what's really important to maybe wrap up this talk is that, you know, like in an optimizer, these optimization rewrites are, you know, cost-based, heuristic-based. They're not really rule-based because, you know, if you always do a skew rewrite, you're going to pay extra CPU if you don't have skew. So we need more of automating it. So this is a very high-level architecture of what we call the statistics store that we built for F3, and where this serves like a producer-consumer kind of model, where we gather some statistics and we capture it in a store, and there are different elements that can consume that. But in a high level here, initially the simplest way of dealing with this statistics store is that users on call can write to this store directly. That's maybe the simplest way to actually get these optimizations. The more advanced, the more automated way, if we get this information through an offline process that go through the logs. So this is kind of after the fact, looking at the history and trying to extract statistics. So if the request or the pipeline is recompiled, or if the feature specification is recompiled, then we can get the optimizations. So this is the main idea. We really want to automate these rewrites through collecting statistics. And we get this, I mean, the initial thing was after the fact, which is based on history. And we are moving in the direction now of trying to actually do it proactively, which is trying to get these statistics even before you actually do the compilation. So yeah, overall, we have accomplished quite a bit in this F3 optimizations. We have handled the null skew and the non-null skew as well. From the automation, we have built the statistics store that we are trying to also keep it in sync with the general, what we call the metadata for DI, for data infrastructure, because there's an overlap there. So we have this asynchronous write path that actually goes through the logs and collect statistics. And on the F3 side, we're consuming this in the optimizer. In progress, we're applying the optimizations, the rewrites, and the statistics as well, the automation for the group by in the case of you're doing aggregations. And we're also extending this notion of skew to expressions, because many times when you do joins not on a base column, but you do it on a SQL expression. We're also implementing the top K that Hanuman described. And we have other rewrites that maybe too detailed for this talk here. I think that's it. If you have any questions, let us know.
Thank you. I don't see any question. I may I have a few questions. How do you handle backfill?
That's maybe a general F3 question. You mean for relative to the optimizations or in general here?
How do you automatically trigger recomputation or statistic
Uh,
when backfill is done?
this is, yes, statistics for everything that's been executed. Right now, we're focusing reactively on the history. So for backfill, it will be covered with what we call the proactive mode, which means that we get statistics for before we execute or for new data or new pipelines. Does that answer the question?
Yes, thank you. Okay. Thank you for the talk. Our next talk will start at 2:15, so we'll take a break.
All right, thank you.
Thank you. Okay.
Can you see my slides?
Yes, welcome back, everyone. The next talk is from Twitter and features Sandbox.
Thank you. Hello, everyone. Thanks for joining this talk. Today, I will be talking about ML Feature Sandbox. My name is Nasran Gedar, and I'm presenting this work on behalf of the work that my team has been doing on ML Feature Sandbox. So these are, I'll be talking about a couple of tools that the team has developed and why we think it's very useful. So before going into details of this talk, I would like to share the agenda with you. I will start by going over the feature development process in our ads prediction models. So what are the steps that from ideation to productionization of a feature that we take into our ads prediction models. Next, I will be talking about the different steps that are involved involved in feature evaluation. So based on the feature development process, there are different steps that we can evaluate and basically improve our processes in. Then I will be talking about where we want to apply faster feature iteration and why it matters. So from the end-to-end life cycle of a feature, where we can make improvements and why we think improvements are necessary. Then I will be talking about automated offline feature evaluation. And then I will be talking about automated online feature evaluation. So there's distinction between offline and online feature evaluation. And for each of them, I will be talking about next steps. And hopefully in the end, we'll have some time for any questions that you may have. So let's go into the feature development process. As you can see within this graph, there are different stages and steps involved in bringing a feature from ideation into production. So if you look at the top process, first we start with ideation and data preparation. So for any signal or feature that we think might give us some clue and some positive information in our ads prediction models, we start by gathering data, seeing how reliable the data is, and thinking about what sort of features we can extract from the signals and the data that we have. So we can have different type of features. For example, we can have embeddings. We can use the raw signals as they are. We can aggregate these signals into counting features that could be used both for the users and ad. And we can have interactive features that is capturing the interactions between the users and advertisers and use these as signals for our prediction models. So once we have come up with an idea and we have gathered the data, we need to implement the feature. So this is the feature engineering step where we think about feature implementation, how we are going to use that feature. Are we going to aggregate? Are we going to use the raw signal? And basically coming up with the best featureization method for that specific signal. And next, we will do feature experimentation. So feature experimentation is where we do some offline analysis and see whether, make some estimations, whether this feature is helpful or can give us better outcomes for that prediction model. And finally, if we get a good green light from the feature experimentation, we go into online feature iteration, where we bring the feature online. At this stage that we have worked on the feature and we have gathered some green light that this feature is useful, we also would like to have a feature catalog. So basically, we have different prediction models and each of them have their own different set of features. But we want to make sure that we have the necessary information to duplicate or be able to track these features in the future. So we have the feature metadata, some of these offline gains and information about the features cataloged somewhere so we can have access to it in the future and make actionable predictions in the future. So on the other side of the feature engineering is the model engineering. In the model engineering, we have offline and online steps. For example, we will do hyperparameter tuning in the offline setting. There are times that when we add the features offline, we don't see gains immediately. So we need to tune the parameters and rerun the experimentation to get to good gains. We will do model tuning and model training. And once all of these steps are done, we have different prediction models based on the objective that we are interested in. So it could be a mobile app promotion, it could be a brand, it could be brand awareness, it could be web, and it could be like dynamic product ads. So depending on which prediction ML model we are targeting, or we think that this feature is useful, we will run online experimentation within that specific model and recheck that everything is looking properly. And if so, we will deploy that model into production. So as you see, there are a lot of steps involved in the feature development process. But if we want to think about feature evaluation as many steps that were involved in the feature development process, there are steps involved in the feature lifecycle. So if you look at this funnel that we have on the right, like roughly, we talked about ideation, problem discovery, we talked about offline data preparation, offline evaluation, feature iteration, where we're saying that by the first try, we are not seeing gains, but maybe another representation, maybe another form of that feature, or like parameter tuning can help with the model gains. So we need to rerun that part. Then we do online feature hydration, which is bringing features into prediction service. Finally, online experimentation, and if everything looks good, we do the deployment of this model into production. So within each step, there are things that we can do to evaluate our features. There are steps that we need to take to make sure that the data and the results look okay. For example, when we are gathering the offline data, we need to make sure that we have good coverage, the data is reliable, and the answers that we're getting are reliable. When we are getting offline model evaluation, basically we need to make sure that the gains look good, at least in an offline setting, so we can go online and iterate on the features. When we want to basically do the online experimentation, we need to make sure that the feature is also okay in terms of cost and latency. So not everything is cheap and not everything is fast. So we need to make sure that if we add that specific feature into production, that will not break our system, and we can add that efficiently into the prediction service. So there's a lot of steps involved in evaluating that feature over time. And even after deployment, we need to make sure that we look at these features over time. So we have like a health check set up properly and can basically track any features that are not working properly over time. So I talked about why faster feature iteration matters, and think about a scenario where we have a ton of different features, a ton of different signals that different teams or different parts of the company is interested in, and they want to experiment with these, and they all think that these features are helpful. How can we prioritize these features? How can we make sure that the evaluation is fast enough that they can all experiment with these features, or make sure that if they abandon these ideas, they were not bringing a lot of gains to the models. So that's where the faster feature iteration comes in. So basically, we just said that in terms of ideation, when feature requests are coming in, and a lot of times it's just a hypothesis. People are not sure whether there's data to back that idea, there's data to back the impact. And we need to, for every case, case by case, we need to discover data that justifies these features to be added into the models. And usually, as you may imagine, there are more feature requests that one team can experiment with. And we have different prediction models and different type of signals. So, for example, we have contextual signals, we have signals that are on platform, we have signals that are off platform, we have semantic signals, And if we were to experiment one by one on these signals and add them like one by one to different models, it will take like limitless time, and also it will not be efficient. So if we were to have a way to evaluate the impact of a feature in a timely manner and have like a green light really easily without needing to know the model challenges, without needing to run the whole experimentation ourselves, make adjustments to the code, it could be quite valuable in terms of making the process faster and more streamlined. So as a solution, we have started focusing on 2 steps. One is offline feature evaluation, where we want to make sure that we can prioritize the right signals. We want to make sure that we have good gains without going into the problem, without spending time on bringing the features online. And for this problem, we have built the feature evaluation sandbox. Basically, in a nutshell, the sandbox is used for running automated feature importance. It gives us a measurement on how much a feature can contribute to the ML model prediction and evaluate its usefulness into our GCP models. The way that we are thinking about currently that we are calculating the feature importance is by ablation study. So if we were to have, think about it as having that feature in as opposed to having that feature out of the model. Basically, calculating the model metrics by having that feature in the model, and then another time calculating the feature metrics, the model metrics without having that feature in the model, and repeating that process for different features, which can give us different scores. And by comparing these scores, we can kind of get a signal about the importance of these features if they were to be added into that specific model. But keep in mind that because we are doing the ablation study, it means that this is model dependent. So we have to start by like doing this for a model and then expand this into different GCP models. So we have created this sandbox with a goal in mind that it is easy to use, like different people do not need to know the model challenges, the details of different models. So basically by having the results in a Google Cloud storage, people can just decide on the usefulness of that feature. So results look something like this as explained in this page. So we will show the name of the removed feature, the corresponding model metrics, how much of a byte size we have removed by removing this feature, the AUC, which is a performance measurement for classifying problems as at different threshold settings. So people can see the results on how it looks for different thresholds. RCE, which is a prediction accuracy metric that we commonly use for our prediction models. The loss, which is a measurement of model quality impact, scaled by the byte size of the feature. Basically, when that given feature is removed and when it's not. So it will help us incorporate the impact of the model quality on the impact on the model latency based on the size of the feature. So giving all of this information to the user will help them by giving them the go ahead or not go ahead on that feature, specific feature. And the main challenge that we wanted to fix here was to build a system that is easy to use for people who have no idea about that specific model. So basically, if a user discovers a feature that they think, for example, for one of our models here, it's the P-video model, it's helpful for that model. Let's say like number of views on a specific ad can give us some clue. And they have some idea, they just know that there's some feature and some data in a BQ table that can be used for assessing that feature by having the table and by having the basically a name for that feature. we can give them the impact or the estimated impact of that feature in that specific model. So we try to minimize the effort that a user needs to do to get like results, and that has simplified the task very immensely. So what are the results? So we have automated this process. Basically, any hypothesis can be tested, and we can see if that improves the GCP model and has a positive impact on the gains of that model. So if that for the system, if that specific feature is increasing the model RC by some threshold that we have set and is like agreed upon by different teams, we say that, okay, this feature seems to be a good candidate. Let's take it up. Let's prioritize that, and let's work on including that into our models. And usually when we have good indications for one model, for a feature in one model, it means that there's a good chance that this feature may also have good impact on different models. So basically, we are multiplying the effect of that feature. And our goal as the next steps is to make this process automated end-to-end for different features and different models. Handling different feature types can be challenging. So some features are easier in nature. They are numeric, they are just like binaries, they are easy to deal with, and some features are harder, like embeddings or aggregated features, which are a combination of different features. So we want to make sure that we are able to automate this process for different feature types and different models, because as you may remember, this is model dependent. So we want to make sure that we include all of our GCP models for this feature offline evaluation. And the other part is that right now, what we're doing is that we're doing an ablation study to get some signal about the importance of the feature. We want to make sure that we have other techniques of evaluating a feature's importance, and not just by leaving a feature out, maybe supporting groups of features. Because if we were to support groups of features, it means that we are also catching the correlation between features. There are times that features are important, but because they are correlated, when we add them, the gains are not cumulative. Which means that we have missed the correlation between the existing features and the new added features. And by having supporting groups of features, we can avoid this like non-added gain in the future. So I talked about offline feature evaluation, which can give us a heads up or a green light for going into online mode. But why did we start working on online feature selection? So let's say that we have built a model, we have some features in the model, and now our models frequently contain deprecated or underperforming features. Why? Because new features come in, better features come in, data becomes unreliable, and there are times that some features have been very useful in the past, but they are not anymore. So engineers have to spend countless hours just evaluating the models and make sure that they are removing the low-performing features. And we want to make sure that we have a way of identifying these underperforming features and basically give another signal to modelers and engineers that these features need to be deprecated. And basically, with this tool, we want to make sure that we are providing that signal and enabling our engineers to remove the low impact features. So as mentioned, why do we do feature selection? So as I mentioned in the past slide, features are the data that you give to your ML models. And if selecting the correct feature is a key aspect in training ML models. And there are times that features and their sizes can impact the model serving performance. So it's not just about the model quality, but also serving performance, which is the latency and the cost of these features. So there are times that some features are to some extent bringing gains, but at the same time, they are very costly. So we need to make sure that we keep track of those costly features and remove them and substitute them with features that are more reliable, at the same time less costly, and bringing similar gains. And so by removing the features that are not important to the model, we make the models more robust by improving latency, by making the models better, like predictions are better. We allow models to serve more performance sets, so with higher click-through rate or lower cost. And overall making improvements both in terms of the model quality and model performance. So after thinking about why it's important to have online feature evaluation, we thought about that let's have this also automated. We see a lot of benefits in automating the online feature evaluation. Basically, by launching a model into production, in the past, we used to not have any way of tracking this, the feature importance over time. And as mentioned, features can decrease in importance over time as they may miss data, they may be updated, there may be similar features with similar information. Just as an example, we had to clean up like 50 plus features in recent time from like one of our map models because they were not as useful as before. So by having a proactive way of finding these underperforming features and the important features, we can drive these changes more automatically and make sure that the engineers do not need to manually go and check and have a way of processing these with having the latest feature importance data. So by having this logic, we built an online tool, which is called the Feature Importance Tracker, to do online feature evaluation. Again, this is model dependent, so we need to extend this to all of our GCP models. Basically, we have recurrent jobs that tracks the importance and quality of features over time. And gives the results as a dashboard, as well as sending the results into email accounts of the engineers or modelers. So there's a way that they can understand whether the feature importance has changed, or if they want to like dig deeper, get more insights into the feature, they can look into the dashboard, as you can see in this page, and get insightful information about the features. They can compare different features, look at the history, see if the most important features have changed over time, and a lot of other insightful information just by looking at the dashboard. So by having this tool, our modeling teams had a few advantages. One advantage was that we improved model serving performance by making it available for engineers to discover features that are not relevant anymore. We improved and increased cost savings by helping making cleanup decisions on features that are no longer cheap. We enable easy feature discovery. It is also helpful to see that how features are acting over time, so ML engineers can take advantage of the feature qualities over time. And we simplified feature health monitoring, basically by having this dashboard and sending out alerts automatically to different modelers. We have enabled the health monitoring over time, making sure that features stay healthy and increase engineering velocity. So there's a ton of effort going on currently around how much improvements we can make in terms of model quality, feature cost, and by having these steps automated, we are saving a lot of times and that historically have been manual. So in terms of results, just like offline feature evaluation, we have automated this process. We are sending notifications to people about the feature importance, about their impact, And basically, we are giving a thumbs up to people who wants to deprecate low cost, low impact, high cost features and improving model quality. And just like offline feature evaluation, our goal is to automate the online feature evaluation process for all of our GCP models. Again, this is GCP, this is model dependent. So we need to make sure that this process is automated for all of our models, as well as different feature types. And basically, again, we have one method of evaluating features online. So again, by removing that feature, gathering metrics, and doing that process with all of the features, this is the way that we're doing it right now, but we want to make sure that we can handle groups of features, we can handle different methods of gathering signals on importance of the feature online, and give that ability to different model owners to experiment with different methods as well as different models. Right now, the deprecation process is still manual. So if model owners find out that this feature is no longer valid or no longer high impact and want to deprecate that, this process is now manual. So they have to manually delete that feature. But we want to make sure that we have this end-to-end process where deprecation also becomes part of that alert system, and we are able to delete any features that are not impactful anymore. And by doing so, save cost and keep the quality high. So that was it from my side. Thank you for listening. And if there are any questions, I would be happy to answer.
There is a question on the chat. Can you read out the question and answer them? Thank you.
Sure. Can you share the question? I'm not able to see the question.
It's in the Q&A window. Go back to the Zoom session, and then there's a Q&A button.
Oh, I saw. Thank you. Yeah, so we run the evaluation impact tool daily, actually, and we send out alerts like weekly. Yes, we have measured the running cost of the evaluation tool. Right now, the cost is not as much, so I think it's about $5K or so for a month, which is, I think, very low. We have to calculate them on the fly in terms of like pre-calculation. So for the online evaluation, we have to calculate them on the fly. For offline evaluations, they are pre-calculated. Does that answer your question, Hangfei? Great, thanks.
Any other question? We have 1 minute before the next talk. Any other question? Thank you.
Thank you.
So our next talk is from Netflix on scaling for recommendation model.
There you go. So, hello, my name is Pablo Delgado, and I'm here with Kabir Nagrecha. We are going to present one optimization work that we did on one of our models. And the title is the Scaling Out Data Loading and Pre-Processing for Training Recommender Models. So the agenda will see, we will talk a little bit about Netflix and how this model plays a role in one of our recommendations. Then we will do explain how this is a tiny model that has big data. And we will do two analyses, one of the gradient sparsity and all reuse, and how we improve the I/O by deploying a data service to ingest data. So in Netflix, everything is a recommendation. For that, when we construct the page, we choose the rows, and the rows are being selected by an algorithm. Also, the videos that you see in the row are sorted and presented by another algorithm. So everything that we use in the page is powered by an algorithm. Okay, one more. So even the artwork, depending on the profile who's visiting the page, we might surface one artwork that is different from another. So one such model is very tiny in comparison with the amount of data that we have to ingest. In this example, we have a model that is called Deep and Wide, quite, not quite, but it's a fairly small model of 3 million parameters. And we need to feed it 2.5 terabytes of data per epoch on training. Turns out that when we do that with only one GPU, we spend 13 hours to train on a single GPU. So we said, let's see if we can do this training in parallel with many GPUs. And we try with 2, and then you add more hardware, or you parallelize the process, and you still take the same amount of time. So something was wrong on the parallelization that we did. So we need to investigate. And this is also surfaced in one issue in TensorFlow, but it's related to the way we use the embedding tables. We're going to disclose this, how this works in a minute.
Right.
And Kabir will explain a little bit about it.
Yeah, so I'll be talking about some of the issues we saw with sparse gradients for embedding tables and how they interact with all reduced patterns and data parallelism. So before I go into that, I'll just quickly recap what sparse gradients are and why we even need to use them to begin with. So in recommender models, it's very common to use these embedding layers. And for anyone who's not familiar, embedding layers are essentially very large lookup tables. They'll match certain entity indices to output vectors. So those indices could correspond to maybe different videos from Netflix's catalog, or different countries from a different region. Now, the problem with the embedding layer is it's very wide and it consumes a lot of memory, but it's also very fast because the only operation that needs to be done here is a simple lookup. Now, because of the width of the model and its memory usage, when we're running training and we're trying to apply gradients to update the embedding table, if we did this normally, we would end up with a very wide gradient vector that's consuming a lot of memory. But if you think about it, in a given batch that we provide to the embedding table, we're only accessing maybe a few indices at a time. In a total batch, you might access 1% of the total indices. So all of the other indices of the table that weren't used at all in the training, they essentially have zeroed out gradients. You've got a very wide vector to match the embedding table size, but only a few relevant data points. Now, the problem with this in the context of data parallelism is we'll be synchronizing these gradients from GPU copy to GPU copy. So wasting the bandwidth on this useless zero data, it'll slow down our model for no reason. So the traditional solution has been sparse gradients. The idea behind sparse gradients is you're essentially getting rid of that unnecessary zero data and compressing down the gradient to only its important non-zero features. How we do this is we store the gradients as basically key value pairs, mapping indices to relevant gradients. We'll record the indices that have actually been used in the embedding table and map those to the gradients that will be applied to the corresponding indices. All of the excess indices, we no longer need to store their 0 gradients. Now, on the surface, this seems great. You know, we've saved a lot of space. There'll be less data that needs to be transferred between GPU to GPU. But there is a problem with this approach. In standard data parallelism, the way you'd synchronize the gradients is an all-reduce pattern. You'd have the vectors, you'd reduce them onto each other, probably using a ring all-reduce. Ring all-reduce, it's known to be efficient, and it's been proven to be bandwidth optimal for reduce patterns. But when it comes to sparse gradients, this sort of pattern no longer works. And the reason is that now we have this slightly more complex representation. We don't have standard vectors anymore, we have index gradient pairs. And across different GPU copies, those indices could be different, they could be the same. So we can't just directly reduce these index key value pairs onto each other. You can't map index 0 with index 30. Summing those indices together will make no sense. So instead of doing an all reduce pattern, it's required that we do an all gather pattern, which includes an all to all step. Every GPU will communicate its gradient, its local gradient copy, to every single other GPU. So while we're benefiting from sparse compression, we're now adding communication overhead because we're forced to resort to an all-to-all instead of an all-reduce. Now, this is only the start of the problems with sparse gradient representations. After the gradients have been all-gathered, let's say we're looking at a single GPU after the all-gather state, it's now gathered in all of these copies of sparse gradients. Now, the question is, how is it going to combine these sparse gradients? Well, unlike a reduce pattern where you can just add them together, we actually have to go through a complex deduplication procedure. We start by concatenating all of the index gradient pairs. But after this, we now have to identify potential duplicates because different GPUs might have produced different updates for the same indices. So once these duplicates have been identified, we now have to fold them onto each other in a deduplication step by aggregating the gradients for the matching indices. So in exchange for having this sparse compression, we've added all these excess costs of an all-to-all complex deduplication procedure that simply aren't present for the dense all-reduce. Now, what we're seeing here is a trade-off. We're seeing some benefits from using sparse compression, but we're also seeing some downsides. So what's necessary is that we identify the point at which the benefits of sparse compression actually outweigh the deduplication costs. So we ran an analysis to see at what size of embedding table sparse gradients actually end up outperforming dense ones. And the interesting thing is that traditionally for embedding tables, sparse gradients have always been considered the default. You just go with sparse gradients all the time. Most training frameworks will use sparse gradients under the hood for any embedding layer. But what we found with our analysis is that sparse all-to-all only outperforms dense all-reduce once you hit a table size of about 50,000. Now, this was in fixed conditions, so this needs to be evaluated for every specific application. But there is a trade-off here, and there's definitely points where a dense all-reduce is still better than a sparse all-to-all. In fact, for the model we were trying to parallelize, it was quite small. So it turned out that using the dense all-reduce, despite the inefficiencies of the excess zeros, it was twice as fast as using a sparse representation. Fortunately, the data parallel training system we were using, Horobot, it supports force converting these sparse gradients into dense vectors for the all-reduce. So that helped quite a bit in implementing this change. Now, there's again a trade-off here. We're suffering through the added costs of having all of these excess zeros. We do have to communicate them from GPU to GPU, but that on its own is outweighed by the benefits of using all-reduce over the all-to-all. Okay, so I'll be passing it back to Pablo to talk about, oh, there's one more thing. There's another approach that we've been looking at for the future, which is table sharding. Rather than using replication of the tables in a data parallel format, another option which has been gaining popularity has been to partition the table across multiple GPUs. Now, the benefits of this is that if your table is very wide, it's consuming a lot of memory, you're no longer bound by the GPU memory limitations of a single GPU. It does induce an all-to-all step, because the idea is that while your table is sharded, the model that could be on top of the embedding table, consuming the embedding vectors, that is still replicated in a data parallel fashion. So to convert from the outputs of your table, the model parallel table, to the data parallel copies, we still have an all-to-all step. So this is something we're still looking into for the future, if it will still benefit these smaller model architectures, just as it's benefited the larger embedding tables. And yeah, we're hoping that this could be a direction we go in the future. So I'll give it back to Pablo to talk about the TensorFlow data service.
So to recap, now that we have sorted out the parallelization problem, so now we can get multiple GPUs to resolve the training issue. We now need to feed those GPUs with a constant stream of data and hopefully keep them busy most of the time. For that, we implemented a TF data service, which comes with TensorFlow default. So this is a little diagram that explains if you have a GPU instance and you have only one GPU training with TensorFlow, we have an arrangement of an S3 bucket where we have the training data, and in front of it we put a file system called FSX for Lustre that comes with the offerings of AWS. And what it does is read ahead cache from S3. So it provides a better throughput for the data that you can read from S3. And it's distributed so we can read it from every node in the cluster. So what we did with the TF data service, we can see it again. We took the TF data experimental dispatcher and data workers, which you need to deploy in front of TF worker, and we abstracted away and we call it data service. And what it does is it deploys a dispatcher for you and a number of data workers that will read the stream of data or the files into the dispatcher and feed the TF worker. Can you go next? So now we can have multiple workers, each worker depending on one dispatcher, and every dispatcher depending on many data workers. With this pattern, we shard the data into the number of GPUs that we are going to use. And in turn, so every dispatcher will handle a shard of the data. And in turn, every data worker will manage to get a fraction of that data and push it into the dispatcher. This pattern is also good for, we can offload the data workers into its own CPU box, represented by partition this in a vertical line. So we have a CPU instance where all the data workers will just consume the data, batch, and pre-transform, parse the data, and the dispatchers will ingest from local data workers and remote data workers. That pattern is it's made so we can also utilize the extra idle CPUs that live in the GPU instance while complementing the extra CPUs that we need from another host. If we keep going on this pattern, we can probably do also multi-machine, so multi-GPU instances where you want to escape the boundaries of one training machine. And you can solve multi-CPU instances, multi-GPU instances, and this will give you the scalability that you need. Conclusions and future work. We went from 6 hours of training to circa 30 minutes. We had a lot of improvements on the velocity of experimentation. This also will give us a faster model selection when we have to do hyperparameter tuning. We can do many more points than before in exploring the data. And we also can add more data from 2.5 terabytes in 5 minutes. We can go to larger data sets if needed. Also, faster is cheaper. The way we train and the way we use cloud services, we are billed by the hour. So the less time we spend on the machines, the less time, the less money we will spend. And also, there is a counterintuitive fact that if we add a CPU instance, we might spend some more money. But spending more money speed up the process, so it ends up being cheaper in time. So we save money in the end. We also will deploy this in different type of GPU instances to compare the price reduction and or the speed gains depending on the use of these models. I think that's all we have to offer for today. I think we run short on time, right?
Yeah, time.
Actually, you still have plenty of time. So there are some questions in the Q&A window. Please read aloud the question before you answer them. Thank you.
We're currently using TensorFlow for this setup. The general structure and the idea of converting for sparse to dense, yeah, that's true for both TensorFlow and PyTorch. And for the hybrid model data parallelism, yeah, TorchRec would be a good option for that.
TorchRec and
NVIDIA's huge CTR.
Huge CTR are the two contenders in that space.
And the second question, people usually have other NN layers after embedding, which are not sparse gradients. How do you all gather embedding layers and do all reduce on the rest NN layers at the same time? So the idea would be that you've got the, you're doing all reduce on that portion of it, but then the sparse gradients on the embedding layer specifically, you do all gather. So it's not that the whole model is doing an all reduce at once, partial would have to be an all gather for the embedding layers. Sparse gradients, you can't run all reduce at all. So that's why it's necessary.
So I think the question was if we have two. So yeah, when we do in the optimizer in Horobot, we select convert everything sparse to dense. We end up doing everything dense in the all reduce stage.
Are there any other questions or follow-ups to those?
I see another question.
The data order consistency, I think that's...
Yeah. So the initial idea is that you shard the data in disjoint data sets. So every GPU will see a different mutually exclusive subset of the data. Together, all the subsets will give you back the original data set. The TF data dispatcher has an option that has a configurable semantics. One of them that is the one we are using is that you want to make sure that the shard that you're taking care of, the workers in that shard, will expose one element and only one at a time per epoch. And that with that you make sure that you visit within one epoch, you visit all the elements at least once. But the ordering is not. We in the model that we're using, we don't necessarily need a data order between elements. Actually, we shuffle the data per epoch before we start training and per epoch. So we don't rely on the ordering.
I believe in our setting, the stochastic gradient descent is robust against data ordering, so it doesn't matter as much for our application. Oh yeah, for the CPU instance. Let me go back to that slide.
So for the amount of data that we need to ingest, so the model is so fast that the amount of data that we need to read, it's consuming more CPU than other models. Or maybe if I say it in a different way, in order to consume the data at the speed that we need, we consume a lot of CPU. So offloading to another machine, and it's like expanding the number of CPUs that you need per GPU. And that gives you the throughput that you need to keep the GPU busy.
Right, yeah, because our model is so small, we can't easily overlap the computation, the processing on the CPU with the GPU execution. And so we need a lot of parallel workers for the CPU, and often will be bounded by the CPU limitations of the GPU box. So that's why we need to scale out further.
It's another follow-up question.
Oh,
Scroll down.
We currently are using TF data records, so no, we haven't looked at Petastorm. Since everything in our infra today depends on Ray, we have a Ray cluster to manage the TensorFlow training. We might use Ray datasets to ingest Parquet files. But yeah, it's something we're going to explore in the future.
And in regards to the caching, I believe the issue we ran into is that the memory wasn't sufficient for caching even across both instances.
Yeah.
So we have to stream the data. So it's actually for the CPU scaling out the processing across multiple CPUs more than caching in memory.
Caching the data might be an opportunity if we need to reuse the same data set over and over. For example, in model selection, hyperparameter searching, we might need to train many models with the same data set. So we might explore some caching idea.
Founding GPU instances. Let's see again. Right.
Oh, so how does CPU instances communicate with CPU instances? Are they the same rate? So these are in the same rate cluster in different nodes. But you need to deploy the dispatcher first, and the dispatcher will gather an IP address and a port. And then with that IP address and a port, you can pass it to any data worker deployed anywhere, and that will communicate with the dispatcher. And the dispatcher will know where the data workers are.
Yeah, the data between the CPU and GPU instances, it's sent over gRPC for the TF data service. We're not using RAY.data right now, right?
No, we're not using RAY data currently. But yeah, the data traverses the boundaries of the machines via gRPC, and also locally between the dispatcher and the TensorFlow worker via gRPC. And I believe now once it's in the TensorFlow worker, it's copied to the device, and we keep also prefetch a batch in the GPU.
Right, so yeah, for the sparse gradients, we were mainly testing the performance of the embedding table layer in isolation for this chart to determine whether the synchronization would be better for the table itself rather than the overall model size. In general, for our model architectures, the recommended ones, the model size is dominated by the table anyway. So in terms of the conditions of the performance, it's largely dependent on the embedding table size, at least in our experiments. And the sparse gradients, in our case, actually weren't helpful because our models are so small. As you can see from this diagram, we saw that they would only be useful about 50,000 entries, and our model was about 5,000 entries. So it's well before that limit where sparse becomes better than dense.
Any other question? Thank you. The next talk will be at 3:30. We will take a break. Thank you.
on the.
Let's wait one more minute till 3:30. Feel free to share your screen. Thank you. Okay, our next talk is from LinkedIn about scaling model inference.
Hello, everyone. Thank you for coming to our talk. My name is Sasha Ovsyankin. I'm a tech lead of LinkedIn model serving infrastructure.
Hi, my name is Dhritiman. I'm an engineer with the machine learning infrastructure org at LinkedIn and tech lead for Model Cloud.
So we're going to, after solving this problem. Yeah. No, you're okay. Good. So we're going to talk about model serving part of LinkedIn machine learning infrastructure. Can you move on? Yeah. So the agenda. We'll give some examples of use cases we have for serving our models, challenges that we encounter, and how do we solve this challenge by using remote serving with the solution called Model Cloud, discuss some production use cases and directions of our future development. So these are some of the use cases that we have for AI at LinkedIn. So search and recommendations, anything that you search on the website, be it jobs, people, companies, comes through the search infrastructure and needs to be scored for relevance so that you would see the most relevant results. LinkedIn feed, same thing. We want to make sure you see the most relevant content that we can put in front of you, the content we think you'd be most interested in. People you may know is our way to predict whether these are the people who you are working with or who you know and you haven't connected yet in order for you to extend your network. Ads ranking, we need to make sure the ads are most relevant and interesting to you. We need to run machine models for that. Content quality models to make sure the content we surface on the site satisfies all the quality requirements. So you can, and these are only some of the examples. You can see that there's a wide range of different variants, different models with different considerations, and that creates some interesting challenges. So here's, we want to go over overall picture of our machine learning stack, and in particular model serving part of it. So obviously you need to do feature engineering, and you need to train your model. And in order to use this model, you would need to deploy it to create a create a certain certain artifact in certain format, put it into repository so that the certain applications will be able to access it. After that, you want to integrate models with your application code and provision the hardware to run this model. Operate this, make sure everything's all right, and track the results of that. Underneath all of this, we have framework that does orchestration of different learning, different inference frameworks such as TensorFlow or Onyx or other types of models. Yeah, so let's look at some of the challenges, or let's look at how we do serving and some of the challenges that users face with that. So, as you can see here, users who access the site, there will be events or requests ending up in some of the service of the site. We at LinkedIn use service-oriented architecture, so all the content providers that we're talking about are implemented with certain services. And some of those services need to run models in order to do their work. So this is an example of such a service. So in order to do that, you need to allocate the hardware, make sure you have enough resources allocated for this service. You need to load the model from model repository. Then you make a call to run inference. During this call, you need to access features, access the data infrastructure to get feature data out of that, run the inference itself, track the results, and monitor the execution. All of these are done different parts and different libraries. So as a application engineer who is responsible for this application, you need to manage the hardware. You need to make sure you are integrated with different parts of the different libraries, and if there are any issues, you need to work through these issues. Work with different teams who provide these libraries to you, and all of this on top of like just managing the overall service as an application engineer. So more challenges are, we know that running models increasingly consumes more resources. Models becomes more sophisticated, so it consumes more resources. So you need more planning to get those resources. You need better monitoring for those resources. You need to make sure many processes happen in parallel so that you could reduce your latency to something reasonable. And when you scale the models, you need to take into account the model hardware requirements. And even when you change, for example, new version of the model, that could require different more hardware. So you would need to scale up the service. So we end up in the situation where we have a certain coupling between application infrastructure and model infrastructure, and this creates even further challenge for the application engineers. So all of this challenges that we want to solve, and our solution is to use remote inference, and the platform that does remote inference, we call it Model Cloud. It contains a unified workflow for the whole serving process. And there's a self-service platform that is managed by a centralized team, by our team. I hand it over to Dridman to dive deeper into the details of the platform.
Maybe you can. Thank you, Sasha. I'll now go deeper inside Model Cloud. Moving back to the slide that you saw sometime back, Model Cloud is a platform that we are building currently to solve all the challenges that you're facing with the status quo. Model Cloud, you can think of as two separate sort of components that work together. One is the workflow. It's a unified serving workflow which sort of orchestrates all the different parts of the model loading life cycle. Essentially, you have to load a model, you have to fetch features, you have to run inference, you have to track features. All of this is sort of should be abstracted through a very unified workflow with a clean API that the user can just interact with. So that we are calling as the Model Cloud workflow. We are designing it in such that it could be run in any application service just by interacting with that workflow. And then comes Model Cloud hosting, which is the platform part of it. When some application wants to delegate inference to a remote cluster, Model Cloud hosting should be able to sort of create that cluster for that use case and then provide all the monitoring and isolation needed for running that use case. So that in a nutshell is Model Cloud. We'll now go a bit deeper inside. So, okay, this slide now actually shows you how we aim to solve the problems that we presented earlier, right? So previously, application service owner would have to sort of do all the integration needed for doing model serving in their own service. But now with Model Cloud, with the remote setup, you'd be able to sort of delegate all of that to a remote cluster. All of the problems of model serving integration would be actually taken care of by this remote cluster, right? And the user would be actually doing only the integration with the Model Cloud API. And with that, all of the problems like managing hardware, service dependencies, issues of model loading, feature access latency, model inference latency, all of that are now isolated to a separate cluster, enabling better decoupling between the application serving challenges and the Model Cloud and the model serving challenges. Moving on, I'll describe two key things. One is the Model Cloud data plane. This is actually the workflow that runs inside Model Cloud. Every request that goes through Model Cloud sort of goes through this workflow. Typically, you would start with the client interacting with the Model Cloud API. As part of the request, you would actually do some feature fetching. You, for example, might want to have some features which are specific to a member. We call them request features. You fetch those features. You pass over all these features over the wire to the server side. The workflow continues there. In the server side, the model would have been already loaded. Once the request comes up, you typically go ahead and fetch the other features that are needed for completing the inference. For example, if it is like a search for showing jobs in your search results, there might be some features associated with each of those jobs. So you'd go ahead and fetch the features of those jobs from a feature store, and then once all the features are resolved, you would actually go ahead and run inference. This would be done using the underlying inference engine. It can be a TensorFlow model, or in future it could be a PyTorch model, and any other underlying inference engine that you're supporting. The inference engine will run the inference, and then finally will return back the results. In the results, we return back all the features that the user intends to sort of get back in the result. So, for example, in the API, the user will be able to provide a certain set of features which they can get back in the response. That's in a nutshell about the Model Cloud data plane. Orthogonal to this is the Model Cloud control plane, which actually talks about how all of this is set up, right? So when you're talking about onboarding to like your use case to a Model Cloud remote cluster, this is what you would typically do. We are designing this as a self-serve platform so that any user can access this platform and use the features provided by this platform to actually provision their tenants, right? So user will typically come to something called a Model Cloud UI. That UI will enable capabilities so that you can create your own tenants. So what is a tenant? A tenant is something which is like a user-facing entity representing a model being onboarded. Contrasting to that, there is something called a pod. A pod is a container which is responsible for running inference. So essentially what you do when you onboard a model to model cloud, we create a tenant and then assign it to a pod. A pod is that pod is like a worker container that sort of runs inference for you. And then based on the scaling requirements of that model, if it needs certain QPS at certain latency, you sort of scale that pod. You can have n number of instances of that pod, and that should be sort of enabled by the features of this platform. So for example, you can scale the pod through your model cloud UI, or you can scale the pod through the auto scaling that we enable, right? So this is like the overall setup. So in this example, you can see there are 3 tenants running. Each tenant is running in their own pod, and each pod has their own scaling criteria. And then there are the clients who are actually calling these tenants from their services. The clients don't call the tenants directly. What they do instead is they integrate with the model cloud client library. That client library in turn knows how to actually call the tenant. So this is the overall picture for the model cloud control plane. And then finally, we'll talk about production use case that you're running. This is an example from search and recommendation use case where the client issues the call. So the picture above is like the picture before model cloud. So the client issues a call to a vertical mid-tier, and that mid-tier then does 2 things. One, it does first is retrieval, and then a set of heavy ranking model. And then after that, there is like a vertical specific inference service, which does L2 ranking, right? Now, what we chose to is like to start with eliminating this vertical specific inference service, which does L2 ranking, and moving that to model cloud, right? So what that will mean is that the vertical doesn't have to now worry about all the model serving challenges that runs inside that L2 service, and instead delegate that to model cloud. What this also enables it is like the heavier models that used to run in the L1 service can now be also moved to model cloud, and instead the L1 retrieval can make room for other features. So for example, you might want to run other type of retrieval algorithms which needs more memory, more resources, which can now be freed up, and now given that the heavier models can be run in a remote system, right? So that's how we are trying to create leverage for use cases at for example, this is like a search and recommendation use case, and model cloud is sort of helping to unblock these use cases, right? So that's the story of our production use case. In future, like these are the things, some of these are already on flight, but we would like to talk about some of the things. So for example, workflow enhancements, like as you can see today, it's pretty much a fixed workflow where like the user, the workflow supports certain things, like it starts with feature fetching and then does model inference, feature tracking. We might want to add more features to this workflow. We might want to compose different workflows to create sort of a DAG so that more complex use cases can be supported. Release assurance is like a capability that you're building, which allows us to ensure robustness of our platform, both from a functional and performance test point of view. Onboarding, operability, and observability, these are like key tenets for our platform. So essentially, like as you can understand, as this platform grows and onboards more and more use cases, we should be able to operate seamlessly and provide necessary tools for both admins and users so that they're able to operate this platform very, very suitably, right? And observability means like we should be enabling all the different matrices and all the different feature points so that we can observe different parts of the system. In terms of key differentiators, GPU inference is something that is growing in importance in terms of its demand at LinkedIn. So GPU inference is something we're hoping to unblock. And we think like by centralizing this as part of the remote platform, this helps to unblock this in a manner so that individual teams don't have to worry about the nitty-gritties of that, right? And in terms of future, we are also looking at moving our setup to Kubernetes. This is in parallel to other efforts at LinkedIn, and auto scaling and auto sizing. These are also important things for any cloud setup. And so we are also focusing on that. So this in a nutshell covers about our future development. Yeah, so to summarize, this is what we talked about. We talked about what are all some of the examples of model serving at LinkedIn, the challenges that the application teams face today with running all the model serving in their own application services, how we proposed model cloud as a platform that solves both the workflow, which is like a API and workflow for model serving, which helps solve the challenges for hosting this cluster in a remote setup. We talked about a production use case, and then we talked about what the roadmap looks like. Thank you, and we'll be happy to take any questions.
There's a question on Q&A. please repeat the question before answer.
Yeah, so there is a question from Jia Lee. For recommendation use cases, it needs to score large number of candidates. Model serving in remote server will send data over the network and incur data survey. What are the resource cost comparison? And is there any comparison? Is there any optimization for the network and the data survey cost? So yeah, so essentially, like this is very much in line with our first use case. The feature fetching that you're having to do is for example, for the entities that you're doing recommendation on. For example, in this case, it's for jobs. So what we have done is like previously in the before use case, all these the features for the jobs, they are actually distributed over a number of feature stores, and that would actually create bottlenecks. So for Model Cloud, for onboarding to this platform, what we did is like we centralized all of that features in one feature store, and that in a sense help to optimize the feature fetch latency for that. You can think of this as with one feature fetch call, you'd be able to get all the features for a particular row, right? And that you need. And then on top of that, you do batch fetching, right? So you don't really fetch, say you are scoring n number of jobs or entities in one ranking call. It's not that you are going to make n different calls to the feature store to actually serve that. You'll be making calls in batches. So essentially what we found out that there's nice trade-offs in terms of like if you make the batch with the full batch size versus you actually split out the batch into multiple batches. Like for example, say if your batch size is X, we found out sometimes that splitting the batch in certain sizes smaller than X and then parallelizing those calls actually helps both in terms of latency and the serialization and the deserialization cost, right? So that's what I can share about your question. Does that help, Jia? Yeah.
Any other question?
There was also a question from Anand. Actually, 3 questions. Yeah. How are tenants isolated using namespaces? How are deployments done for the model cloud code? And are tenants spread across multiple K8 clusters? So I answered them on the chat, but I'll just quickly repeat that. So tenants are isolated within our service infrastructure. So it's a kind of like Docker, but not exactly. And each tenant has its own endpoint. So basically, when you talk to a particular endpoint, you're talking to that tenant. So deployments are done by reusing our service infrastructure, using API of our service infrastructure. So basically, I would deploy it in the same way I would deploy microservices. And in terms of multiple clusters, right now our architecture is built on a single cluster. We may consider spreading it in the future, but for now it is a single cluster. Yeah. You want to add anything?
Yeah, I'll just briefly add on, like for the second part of the question, how are deployments done? So essentially, Anant, like the way deployment happens is that when you deploy model cloud code, it's not necessary that you'll have to deploy it to all the different tenant pods. We have the control to sort of serialize the deployment across the number of pods or do in batches. So for example, we might choose to sort of deploy the code to a couple of tenants to start with, verify any changes, and then deploy it across the different pods. So essentially, it's not like we don't have the control to do that. We do have the control. The way so the application the service infrastructure that we have today, it's an in-house infrastructure that provides isolation such that we can create different sort of mini clusters for each of our use cases. And whenever as I noted, like when you move to Kubernetes, these details might change a bit, but the concept remains the same. Essentially, you have a way to create a tenant for a onboarding entity, and then you assign it a pod. A pod is like the internal container responsible for running the tenant, and then you can scale the pod as much as you want. And then in future, for cost optimization, we might actually want to bin pack multiple tenants inside a pod. So today we are running a single tenant in a pod, but then like from industry research, we have seen that multiple tenants inside a pod is something that is pretty well researched. So we might get there as well.
More questions.
Okay. Okay. Sure. Yeah, so decommissioning is like, so this is something that we are building the self-serve platform that, so coming back to Anand's question, thanks one more, how to manage the life cycle of tenants, example, decommissioning. This is something the self-serve self-serve platform will provide. Essentially, there will be like a construct in that platform, which will allow you to sort of tier doing this automatically. For example, there are requirements where models which are no more in production, like which are still deployed in production but not really getting used anymore. For example, there is no traffic for a certain amount of time. We want to garbage collect those models, right, and essentially stop using those models. So we might build. So we haven't built these things yet. As you can understand, Model Cloud is a platform that you are actually running. Like we have started some time back, and we'll definitely be looking at building some of these features, but yeah, that's the overall idea. I'll move on to the next question from Zuning. Does each pod run a single model or multiple models in the process? Yeah, as I said, like I think I briefly covered this. Today we wanted to keep the setup simple. Each pod runs a single model. When you come to Model Cloud to onboard a model, we call it a tenant. That tenant is your user-facing entity that you get when you onboard the model, and then you assign a pod to the model. So the pod runs a single tenant, but nothing in the framework is sort of such that it blocks from loading multiple models. The framework is extensible such that tomorrow, for cost optimization, if you want to load multiple models inside the pod, we can do that. So yeah, sure.
Okay, so the question about from Street Party, is there fallback strategy if an inference of Model Cloud fails? So we need to consider here what failures we want to look at. In case of remote inference, the failures are like the most likely thing that comes to mind is that there's a network failure that prevents you from either accessing the network or the Model Cloud to access, for example, the model repository. So in this case, having some processing within Model Cloud is not going to help a lot. So basically, the short answer to this is we'll leave the fallback handling on the application user, so they can run fallback models if the API for model inference fails, and we will be looking for use cases for more cases in there. And then the next one, do you have use cases where features are computed on the fly from the data in the request? Yes, definitely. We have use cases like that. And most of our feature handling or feature access is handled via our internal feature engineering platform. And some vary. So it is configured by the users who create features. So it could be extracting information from the source, or it could be calling other services to get information from. That depends on how it is set up by the user, and it is handled by this platform. I just want to mention that some parts of this platform are we open sourced, and you can learn more about this by going to the website feather.io. Sorry, feather.ai. Yeah. And Feather is, I think, missing the last E. So yeah, I can type that. Hope that answers the question.
Thank you.
Any more questions?
One more question.
Yeah, so there is a question from Gia, like model cloud choosing to have the, what is the reason in this model cloud choose have the client side library compared to the bare RPC interface? What function will live in the client? So as you can see, like one of the goals for model cloud was to abstract the model serving challenges from the user behind a very clean interface. Now, as you can think of, when it gets to RPC, you might want to sort of experiment with different types of RPC mechanisms. Different RPC mechanisms might be suitable for different use cases. And essentially, you want the user to be actually talking in terms of their functional domain constructs. So for example, the functional domain constructs in there, here is my model coordinates, like these are the model specification, these are the features in the model that you would like to input. So you'd rather like to have a very clean API, which the user can interact with rather than the schema, right? Like the RPC interface. The RPC interface might be actually optimized for different use cases. You might have a gRPC, you might have a binary protocol, or even a JSON, right? All of these might vary in shape and form, whereas the outgoing API, which you have like as a model cloud API, that will still remain very consistent and coherent in terms of the functional constructs. So that was the main reason that you went with the model cloud API concept. Does that answer your question?
Okay. Thank you.
Let us know if there are any more questions.
Don't see one. Okay. We have a breakout session from 4 to 4:30. And each breakout session will basically cover a general area like feature store, training,
Okay.
deployment, and serving.
So well done. Thank you for your attention, and see you in the breakout rooms.
Yeah, thanks a lot for attending.
Okay.